Hi everyone, welcome to another video. Today we're going to solve a kinematics problem, and the concepts we're going to use are conservation of energy and circular motion. So in the question, a roller coaster of mass m starts from rest at a specific height that we call h, and from that it completes a full loop, this full circle, and then keeps going. The category that they're going to enforce is that the wheels are always on the track. So the cart basically never lets go from the track. There's only regular normal force. And what they are asking is what is the minimum initial height, h, that you need so that the cart remains in contact with the track the whole way around the circle. So we can ignore friction and we can ignore air resistance. So this is a multiple components problem. And I would say the first thing we need to think about is what exactly are they asking for? They want us to know what h is so that the cart is always touching the track. But what exactly does it mean for the cart to always be touching the track? So they basically want you to convert that into a physical meaning. So how we're going to do that is a way of thinking about it is that if the cart is always touching a track, there is always some normal force on the cart as it's going around the loop-to-loop. And as long as there's some normal force on the track on the cart, like from the track on the cart, then we can say that the cart is always touching the track. So that's just some condition that we're going to enforce. So we're going to enforce that normal force, which does not equal 0, is equivalent to saying the cart is always touching the track. And then that kind of makes sense, right? Because if the cart is not touching the track, then there'd be no chance for the track to exert any normal force on the cart. So this is the first criteria you would have to establish. So in other words, we basically want to say that like there has to exist some normal force on the track, from the track on the cart, the whole time the cart is in motion. Now, when we look at this intuitively, we can tell that the cart is always going to have some normal force as it comes down because there's nothing acting against it. It's just gravity, basically. But as it comes going into the circle, we could have a situation where the cart reaches a certain point and then there's no normal force from the track to the cart, so it starts to fall down. And this could happen basically at any point. It could go to the very top and then start to fall down from there. So we have to look at what would basically be the most likely position where the cart would not have any normal force. And the justification we would say is that it's at the top, basically, because it takes the most amount of energy for the cart to reach the top. And once it's reached this point, it's very easy for the cart to continue going around. So if the cart reaches the top and there's just enough normal force for it to keep going, then it'll once again gain kinetic energy and make it the whole way through the track with there always being some normal force. So the point of interest that we're going to look at is this very top point, and that sort of comes from physical intuition and as you solve more of these problems, you're going to realize where you should be focusing your energy on when you solve these problems. So picking a point like this would just come with practice. The other point of interest for us is where the cart starts, because they want to know what the minimum initial height is. So we're going to have to care about where this point is as well. So those are the 2 points that we've sort of figured out so far. And the next thing we should do is solve this using conservation of energy. Because this is not a linear path, it would be very, very hard to solve this using kinematics equations. You could, but you would have to solve differential equations, which have curved lines. So it's going to be easier to solve this using energy. So we're just going to do a conservation of energy. So energy, let's call this point 1, call this point 2. Energy at point 1 has to equal or be greater than the energy of point 2. Now, I'm going to say equal because they're asking for the minimum value. But if they were asking for some conditional value, then you can say change the equal sign to a greater than. So the 2 energies that are acting on the system right now are potential energy and kinetic energy. So potential plus kinetic. And those are the only other 2 energies acting on the system at point 2 as well. So converting this into the formulas that we have for potential and kinetic energy, the E potential is m times g times h. They give us h. Then the kinetic energy is half mvi squared. Now the potential energy is mgh at the top, and the kinetic energy is half mv top squared. We basically want to know what's going on at this point. And again, the justification is that this is where the normal force is most likely to be 0. So we want to solve for this initial condition. Now, from this equation, you can tell straight away that all the masses are the same. So all the masses cancel out. It does not matter if it is a car or a Hot Wheels car. Now, they also give you certain values. So they tell you that the initial velocity is 0. So we know that this is 0. So just rewriting this equation again, just to clean it up a little, we have g times h is equal to g times h top plus half times v top squared. And again, we're solving for the initial height, h. So this is the term we're solving for. Now there's 2 more parameters in this equation that we don't understand, that we don't have figured out yet, and that's h top and v top. So h top would just be this height basically, and that would just be this radius time plus this radius. It's 2 times the radius. And v-top we also don't have. And the way I would recommend getting v-top is with a free body diagram at the very top of point 2. So when we do a free body diagram, we can tell the car is at this position and it's going around the top of that circle. So we're kind of like zooming in on this area over here. Now, what we see is that there are 2 forces acting downwards, normal force and the gravitational force. And there's one force acting against, which is the fictitious centripetal force. So we can use this system right here to constrain what our speed is going to be. So just writing all the forces in the y direction, what we get is that the normal force plus gravity the force of gravity is equal to the centripetal force. Now, we have enforced that the normal force must be greater than 0. That's something that we are requiring. That's what we said here. There has to be some normal force on the track for us to say the cart is still touching. So because of that, the normal force has to be greater than 0. So we can rearrange this equation. Normal force, which is greater than 0, and it equals the centripetal force minus the force of gravity. So if this condition is true, then this condition is definitely true. And we're just going to substitute in the equations that we have from our formula sheet for the force of gravity and the normal force, and the centripetal fictitious force. So again, I'm just going to rewrite this equation. So we have mg always has to be less than mv squared over r. The m's cancel out because they're the same. And we can bring the r over on the other side to get our expression for v squared. So rg, the speed has to always be greater than the square root of rg. Now, once again, this was what we solved at the very top of the system. So we can call this v top. So there you are. We've gotten an expression for v top, and we've gotten an expression for h top. So we have everything we need now to solve this equation. So again, we're just going to substitute the values in. GH is equal to G H top is 2R plus half V top squared. And V top has to always be greater than RG. So because V top is always greater than RG, we can write this as an inequality. Actually, no, I'm just going to write it as an equality because they want the minimum initial velocity. Keep things simple. So in that case, V top would be the square root of RG squared, which is just RG. So then we get GH is equal to 2RG plus half RG. Once again, the H's cancel out. The G's cancel out. And what that gives us is that H is equal to 2.5 R. And that is our final answer. We have to drop the cart from 2.5 times the height of the radius for it to fully go around. And that sort of makes sense because as it's going down, it's got to go at least 2R because that's the height of the radius. And that extra 0.5R comes from the centripetal energy, which is what you see here. This is that extra amount you need to just go around the full circle. So, yep, there you go. That's the full answer to this question. As I make more videos, please tell me in the comments what types of videos would you like to see more of, if it's classical mechanics or if you're solving force diagrams, so that I can make videos that you like to watch. Great. Thank you, everyone.